having had a brief look at where everyone's at, I think you probably passed me, to be honest. What have we done so far? I've gone ahead and I've found my derivative. Please look at your working right now and look at what you called the derivative. If you didn't call it dA on dx, especially because the question even told you, hey, it's called dA on dx, please change that right now, because the thing that you're being the model that you're working with, it has a specific name. When you have other things flying around in the question, you'll have a question that involves area and volume and height and all kinds of other things, right? You need to be able to distinguish between them. If you don't call things what they are, you're going to just land yourself in a lot of trouble. I've got my derivative. Some have wanted, how did I get to this point? I factorized out the common factor of 2 right here. So that turns my 1/8 into a quarter. And then I've said, oh look, there may be a turning point at x equals 5. There's definitely a stationary point, but I haven't determined its nature yet. That's why I went to the second derivative, and hopefully you found the same thing. Okay? So my actual answer to part C, what is the x value that makes a minimum, is this, except think back to the first half of this lesson. There's something that I've left out. Think carefully. We made a headline about it as well. There are constraints on the situation, right? There are constraints. You can't have, for example, like a wire of negative length. And you can't have a wire of infinite length either, because how much wire do you have to play with? 10. There's 10 meters, exactly, right? So therefore, and this is so sneaky, it's why I just blew right past it to see how many of you would notice. There is a constraint baked into this that no one said anything about, but it's there in the question, right? Number one, we said you can't have a negative length of wire. So that means that x has to be positive, greater than or equal to 0. But in addition to that, you don't just have like whatever amount that you want to play with, you've got this as a maximum. So that means x has to be less than or equal to 10, which of course we could include in one single inequality. You could say that that's 0 is less than x, less than 10, and I've included my boundaries, okay? Now, just as a very, very minor point, it's worth having a very small discussion about whether we should include these boundaries or not. I've written them with boundaries. Does anyone think we should exclude them? Like, should we write this instead?
I'm going to say we should include them.
Include?
Finite length.
There's a finite length, so it's like, oh, I can get up to 10. It's not like an asymptote or anything like that.
You could get 0 on one side and 10 on one side. So it could be equal to.
So, Seren, you're saying like I have no wire over here, and I just have one square over here? Well, what are you thinking?
Maybe it should be like not equal to 0, but it can also be equal to 10.
It cannot be equal to 10 because you wouldn't have wire left.
Yeah, sure, because it can't be equal to either.
So, okay, this is really interesting. All right, so what I'm going to say is, practically speaking, it doesn't matter a whole much in this particular question, right? But just there's a very, very small thing. Just go back right to the start of the question, back to the start. This is one of those times where you've got to interpret language here and think about what does that mean mathematically. You've got to sort of translate. How many squares are being formed? 2 squares. 2 squares. If I used all 10 meters on this first square here, what would you have left to make this? So you'd only have 1 square, right? So actually probably to make 2 squares, you can't include these, right? But at the same time, I want to understand like, well, do the endpoints give me something meaningful? So you've actually got to substitute in something, so it's the 0 or the 10. Which I actually do want to quickly test with you right now. Let's just go ahead and see what happens. If I did include these endpoints, right? Hopefully you can see at 0 or 10, you're going to get the same result, right? Why? You're going to get the same result if you had 0 or 10. Why is that? Because you either have this guy as a square, and nothing here, or you have this guy as a square and nothing's there. So you have the same square either way, right? So here I'm going to test my endpoints. Or in this case, it's just an end point, right? So I'm going to test x equals 10. I've got my model way down over here. So help me out. If x equals 10, what's a going to be equal to? 25 you've already evaluated. 25 over 4. This is an area, so it's in square meters, okay? I actually haven't done this already. Maybe you're already ahead of me. I haven't tested what happens at x equals 5. I know it's a minimum turning point, but I don't know what it's equal to. Has anyone substituted x equals 5 into the original function already? If not, please do that now. And I'll hold on because I don't have a calculator on hand.
25 over 8.
25 over 8? 25 over 8, which is half. It's half of this area over here. So this one is clearly smaller. We had to test it just to be sure. I mean, we expected it was a minimum turning point, but as we've shown, just because it's the minimum turning point doesn't mean it's the minimum. There could be some sneaky endpoint which shows it's not the case. All right, so finally, are we done? What's it say? Find the least possible value of the combined areas. That's it, right there. On the bell as if on cue.